Have you ever just stared at a huge cargo ship and thought, how on earth is that thing not sinking like a stone? Or, swirled a glass of wine and seen those little legs, the tears, dripping down the side? Well, it's not magic. It's actually the result of some really powerful, invisible forces that are at play in pretty much every liquid around us. So let's dive in and uncover some of the physics that's hiding in plain sight. I mean, it really is a paradox when you stop and think about it. Steel is incredibly dense, right? Way, way denser than water. If you drop a solid chunk of it in the ocean, it's going to plummet straight to the bottom. And yet, we build these absolutely colossal ships. We load them up with thousands of tons of stuff, and they just float. So, what's the deal? All right, the first piece of this puzzle lies in a force that you've definitely felt every single time you've been in a swimming pool. It's that constant upward push of the water. We call this force buoyancy. But here's the secret. It's not just that water pushes, it's how it pushes. You see, the pressure in a fluid isn't the same everywhere. The deeper you go, the higher the pressure gets. And that means the water at the very bottom of a ship is pushing up with a whole lot more force than the water near the surface is pushing down. So, when you add up all of those different pressures across the entire submerged part of an object, what you're left with is a single net upward force. And that is the buoyant force. It's basically the water itself pushing back against gravity. So, here's the crucial part, and it was summed up perfectly by Archimedes over 2,000 years ago. For a ship to float, the shape of its hull has to push aside or displace a volume of water that weighs exactly the same as the entire ship. Yeah, the steel itself is dense, but the ship is mostly just a giant hollow shell. That shape lets it displace a huge amount of water to perfectly balance out its own weight. Okay, so we've got the ship floating. Great. But that's only half the battle, right? Because a ship that's floating is pretty useless if it capsizes the second a big wave comes along. Staying upright, well, that's a whole other engineering challenge. And history has given us a really brutal lesson in what happens when you get this part wrong. The Swedish warship Vasa, back in the 1600s, was an absolute marvel for its time. But it was too top-heavy. It floated, sure, but it had basically zero stability. On its very first voyage, in 1628, a gust of wind hit the sails, it tipped right over, and sank less than a mile from the shore. Now, to understand stability, why the Vasa failed and other ships don't, we need to talk about two key points. First, there's the center of gravity, or CG. That's the average location of the ship's own weight, and it's always pulling it down. Then there's the center of buoyancy, or CB, which is the center of the volume of water that's been displaced, and it's pushing up. The CG is fixed, but, and this is the whole key, the CB moves around when the ship tilts. And this is where the magic happens. Look at what happens when a well-designed ship starts to tilt. The shape of the part that's underwater changes, right? And that causes the center of buoyancy to shift to the side. Now, that upward push from the water and the downward pull of gravity are out of alignment. They create this twisting force, a torque, that literally pushes the ship back upright. It self-corrects. How cool is that? Naval architects have a specific way to measure this self-correcting ability. It's a number called the metacentric height. Now, you don't need to get bogged down in the math. Just remember this one simple rule. If that number is positive, your ship is stable. It'll right itself. If it's negative, well, you've just built another Vasa. All right, so we've been talking big, right? Massive ships, huge forces. Now let's zoom way, way in. We're going to shift our focus from the properties of the liquid as a whole to the really strange world of its surface, which acts almost like a thin, invisible skin. Think about it on a molecular level. A molecule that's deep inside a liquid is getting pulled on equally in all directions by its neighbors. But what about a molecule right at the surface? It doesn't have any neighbors above it, so it gets pulled inwards and sideways by all the molecules below and next to it. And this creates a net inward force across the entire surface of the liquid. And the result of all that inward pulling is that the liquid's surface behaves just like it's a stretched out elastic membrane. This is what we call surface tension. It's the reason water droplets pull themselves into little spheres. That's the smallest possible surface area. And it's actually strong enough to let insects like water striders walk right on top of the water. This skin also dictates how a liquid is going to interact with a solid surface. If the liquid molecules are more attracted to the solid than they are to each other, the liquid will actually climb up the surface a little bit. We call this wetting. But if they're more attracted to each other, like mercury on glass, they'll pull away from the surface. So, why does this matter? Well, think about something like soldering a circuit board. For a good, strong connection, you need that liquid solder to wet the surface and spread out evenly. If it doesn't, if it just beads up, you end up with a weak joint that's probably going to fail. Controlling wetting is absolutely critical for making countless things we use every day. So, we've seen how liquids can push up, and we've seen how their surfaces can hold together. But here's where it gets really interesting. What happens when the strength of that surface skin isn't the same from one spot to another? It turns out the surface itself can actually start to pull the rest of the liquid along for the ride. And this brings us right back to our wine glass. That elegant, almost poetic thing you see, the tears of wine, is the perfect showcase for this final concept, something called the Marangoni effect. The Marangoni effect is basically a flow that happens whenever there's a difference or a gradient in surface tension. And here's the golden rule, the one thing you have to remember. Liquid always flows from the area of low surface tension toward the area of high surface tension. The stronger skin literally pulls the weaker liquid toward it. Okay, let's break down exactly what's happening in that wine glass. First, the wine creeps up the side of the glass a tiny bit because of wetting, and it forms a thin film. Now, from this film, the alcohol evaporates faster than the water does. This leaves behind a liquid that has more water in it, which means it has a higher surface tension. And what does that stronger skin do? It starts pulling more of the lower tension, more alcoholic wine up from the glass. This keeps happening, pulling more and more wine up, until a droplet gets so heavy that gravity finally wins and it runs back down the side as a tear. And this isn't just a cool party trick either. The Marangoni effect is incredibly important in some really high-tech industries. It affects how molten metal flows during welding and 3D printing, and it has to be controlled super carefully when we're growing those perfect silicon crystals needed for computer chips. So, we've gone on quite a journey here, haven't we? From the absolutely immense buoyant force that holds up a battleship, all the way down to the delicate surface tension that shapes a single drop of water, and even the subtle flows inside a wine glass. It just goes to show you these invisible forces are constantly shaping the world we see. Which kind of leaves us with one last thought. We've just pulled back the curtain on a couple of these hidden rules. But think about it. From the way your coffee climbs the side of your mug to the shape of a raindrop on your window, what other invisible forces are out there, quietly orchestrating the world all around you?